Hello everybody, in today's video we're diving into the concept of conservation of mechanical energy. Imagine, let's say you have a basketball. When it hits the ground, the kinetic energy helps bounce it back up, converting, so it goes right here, and the kinetic energy bounces it back up. This is an example of converting potential energy going downwards into kinetic energy, going back up. This continuous energy transfer is a perfect example how mechanical energy is conserved when gravity is the only actor. Now let's break this down. We'll start with a more explicit image. So now we'll imagine a ball that is only affected by gravity right here. And it starts at position 1, which we'll mark as y1, and it ends at position 2. This will be how and the ground is going to be like right here. Now, if you look back at the work energy theorem, it states that the change of kinetic, that the total work is equal to the change of kinetic energy. So work total is equal to K2 minus K1. From the diagram, we can see that this other force which is doing work on this object, work is also equal to a force times the displacement. Now we just need to find our work, which is, we can see from here, should be mg, and then we have our displacement, which is whatever is the difference between these two. So we'll go to y1 to y2, and then the difference is y1 minus y2. So that's our displacement there, right there. And we'll start by taking this apart one step at a time. Let's grab our equation we drew right here, and as we can see, the force that's pulling the object down is just mg, and the displacement is y1, or yep, and then minus y2. As you can see, this is going to give you a work total of mg y1 minus mg y2. As previously in the last video, we defined potential energy as U of g equals mass times Ry. So as we can see, this is going to be U1g minus UG2. Therefore, the change of kinetic energy is equal to the change of potential energy. Now let's set these equal to each other. So we know that we'll start with the equation work total equals final kinetic energy minus initial kinetic energy. And then we have our potential, and we also know it's equal to the initial potential energy minus the final potential energy. Let's set these equal to 2 together. So we have U1 minus U2 is equal to K2 minus K1. And now let's get the initials on the left side and the finals on the right side. So that leaves us with U1 plus K1 is equal to K2 plus U2. And this gives us the version of our work energy theorem when the object is only being affected by a falling force. We can also break them into their variables here. We know that the potential initial is equal to mgy1 plus 1 over 2 mass times velocity squared, initial velocity, equals to 1 over 2 mass times v final squared plus mg y final position. So those are the units. This equation tells us that that there's a direct relationship between the kinetic energy and potential energy. We described the sum of both both of those as the total mechanical energy, and we write this as E equals K total. So it's going to be your kinetic energy plus the potential energy. And notice how the quantity of total energy is always constant because it's not changing. The total energy is not changing. It's only one's being converted into another, or one's being converted into, for example, a falling object into kinetic energy. This idea is called the conservation of mechanical energy. And now that we have a good idea what this means, let's uh, let's start with a practice problem from our textbook to implement this idea of the conservation of energy. So let's say you have a baseball right here and it's in your hand. So we'll have our stringy hand here, and the ball weighs 0.145 kilograms. And when throwing it straight up, you give it an initial velocity of 20 meters per second from here, and you want to find how high does this go, annoying air resistance. So what is this measurement of displacement on the y-axis? So if we use our work energy theorem from before, we can conclude our final results. We know that final velocity must equal 0 because this is the total height it goes. Initial velocity equals 20 meters per second. And this is always good practice to see where your numbers you're looking at. y1 equals 0, y2 equals h. And we'll use our work energy theorem to solve this. As we know it should be conserved, we'll write k1 minus u1 equals k2, or this is plus, k2 plus u2. And we already know what's going to eliminate. So we know the final velocity must equal 0, so this is crossing out. And we know that the initial position is 0, so its potential energy there is 0. And that just leaves us, this is a mistake here. So the final potential energy is non-zero. The final kinetic energy is 0. So we know that's correct. So that's going to give us 1 over 2 mass times initial velocity. We know our initial velocity here. We know our mass is equal to mass times g. We know g, we know mass. And then we have our y2, which we're representing as h in this problem. So now we just have to solve for h. As we can see from both sides, we can cross out the mass. It eliminates out, the mass is irrelevant. And then we just have to divide by h to get our mystery height in our problem. So 2 times g equals h. And now let's plug in the numbers and solve for our problem here. So you have 0, 20 meters per second squared over 2 times 9.8 meters squared. And that will give us our h here. And it should come out being around, let's see, around 20.04 meters high in the air. And this should be all. Thank you for watching my video today. And if you learned something, don't forget to like the video if you enjoyed it.